Earth as seen from space around 200 million years ago would have appeared almost completely different from the planet we know today. Where the vast Atlantic Ocean exists now, there was only a continuous expanse of land stretching for tens of thousands of kilometers. Most of Earth's landmass was joined together into a gigantic supercontinent called Pangaea, one of the most remarkable geographic structures in the history of the planet. Surrounding Pangaea was Pangaea, the largest superocean ever to exist in Earth's history. It was a body of water almost entirely uninterrupted by continents, allowing ocean currents to transport heat and energy on a global scale. From space, Pangaea would have appeared as an immense deep blue circle encircling the planet's single great landmass. Along the eastern margin of Pangaea lay the Tethys Sea, a vast tropical ocean stretching across the equatorial region. While many ecosystems around the world were still recovering from the Triassic-Jurassic Mass Extinction that occurred approximately 201 million years ago, the waters of the Tethys became a place where life rebounded at an astonishing pace, where many important groups of marine organisms began to expand and dominate the oceans. "200 million years ago, the central regions of Pangaea lay thousands of kilometers from the sea. Some paleoclimate models suggest that these areas may have been as harsh as, or even more extreme than, many modern deserts. Meanwhile, the coastal regions received greater moisture and supported richer ecosystems. Seen from space, Earth 200 million years ago still displayed brilliant white clouds drifting above deep blue oceans, a planet overflowing with life. Yet beneath that peaceful appearance was a world standing at a pivotal moment in geological history. Deep beneath the planet's crust, immense forces had already begun to move. The first signs of change were quietly emerging, signaling that this great supercontinent would not last forever, and that the fate of the entire world was preparing to enter a completely new chapter. From space, Pangaea appeared to be a single enormous and immovable landmass. But if it were possible to accelerate millions of years of Earth's history into just a few minutes, you would see this entire supercontinent slowly being torn apart by the planet's own internal forces. The origin of this process lay deep beneath Earth's crust in the vast, hot mantle, where material continuously moved through convection currents. Movements of only a few centimeters per year may sound insignificant, but over millions of years, they are powerful enough to move entire continents. Around 200 million years ago, heat trapped beneath Pangaea for an extended period began to accumulate to the point that the crust above it was stretched and weakened. The first fractures appeared, signaling the beginning of the end for the largest supercontinent of its time. At first, the changes were almost impossible to notice. The ground slowly cracked apart, and massive blocks of rock sank downward, forming valleys that stretched for hundreds of kilometers. A modern example that helps us visualize this process is the East African Rift Valley, where the African continent is gradually splitting into two parts. But the scale of Pangaea was far greater. This was not the division of a single region. It was the restructuring of nearly all the land on the planet. As the crust became increasingly thin, magma from deep below began rising through the fractures. A series of eruptions lasting hundreds of thousands of years formed the Central Atlantic Magmatic Province, or CAMP, one of the largest magmatic provinces ever recorded in geological history. Geological studies indicate that the affected area exceeded 10 million square kilometers. What is remarkable is that basalt layers of the same age and chemical composition can still be found today in Morocco, eastern North America, and Canada. Although they are now separated by the vast Atlantic Ocean, they once belonged to the same geological system before the continents drifted apart. The evidence is not found only in rocks. Fossils tell the same story. Paleontologists have discovered many identical species of ancient reptiles, plants, and freshwater organisms in both South America and Africa. Their presence on opposite sides of the modern Atlantic Ocean provides powerful evidence that these lands were once connected. Then, as the fractures widened, seawater began flooding into the newly formed lowlands. Small lakes became narrow bays, which gradually linked together into long marine corridors. Over time, the distance between the continental blocks continued to grow. A new ocean was being born. The Atlantic Ocean of today, stretching thousands of kilometers across, actually began as tiny fractures that would have been almost impossible to notice on the surface of Pangaea. This is what makes this period so extraordinary. We are witnessing the birth of the modern world. Every slow movement of the crust at that time was quietly determining the future positions of North America, Africa, and Europe. But this event did not merely reshape the geography of the planet. It also unleashed geological forces powerful enough to alter the global climate and pave the way for one of the greatest turning points in the history of life. Just as Pangaea began to split apart, the planet was not merely changing shape. It was emerging from a biological crisis, that had nearly erased most life on Earth. Around 201 million years ago, the boundary between the Triassic and Jurassic periods marked one of Earth's Big Five mass extinction events. Global stratigraphic studies indicate that between 50 and 75% of species disappeared within an extremely short span of geological time, only tens of thousands to a few 100,000 years. A mere blink compared to the planet's 4.5 billion year history. What makes this event particularly remarkable is that no asteroid has been identified as the primary cause. Unlike the extinction event that later ended the age of the dinosaurs, as the supercontinent stretched apart, enormous fractures opened like cracks, spreading across a sheet of glass under pressure. Through these openings, magma from deep within the mantle surged to the surface, creating one of the largest volcanic systems ever recorded. The Central Atlantic Magmatic Province, or CAMP. Geological data show that CAMP extended across more than 10 million square kilometers, from North America and South America to Africa and Europe, leaving behind basalt layers hundreds of meters thick in some regions. Repeated eruptions released vast quantities of carbon dioxide and sulfur dioxide. In the short term, sulfate aerosols may have reflected sunlight and triggered temporary cooling episodes. Over the long term, however, carbon dioxide accumulated in the atmosphere and oceans, disrupting the entire climate system. Carbon isotope analyses from sedimentary rocks around the world reveal a major disturbance in the carbon cycle, leading to prolonged warming. Global average temperatures are estimated to have risen by approximately 3 to 4 degrees Celsius during peak intervals, enough to restructure the planet's entire ecosystem. A domino effect soon began to spread. The oceans absorbed carbon dioxide, making seawater more acidic and creating severe challenges for calcium shell-producing organisms such as mollusks and plankton, the foundation of marine food webs. On land, climates became increasingly extreme, alternating between prolonged droughts and unusually intense periods of rainfall. The fossil record preserves a picture of disruption. Many large reptile groups that had dominated the late Triassic either disappeared or suffered severe declines. Giant amphibians failed to adapt quickly enough to rapidly changing environments. The oceans experienced a profound restructuring of biological communities. Most importantly, this was not a single catastrophic event, but a process that lasted long enough for each new generation to face an Earth different from the one known by the generation before it. Extinction cleared the way for renewal. As dominant groups vanished, countless ecological niches were left vacant. Sources of food, territories, and biological roles within ecosystems suddenly became available. The fundamental difference from the modern Earth lay in a factor that seems deceptively simple: distance from the ocean. Today, the oceans cover more than 70% of Earth's surface and act as a vast thermal buffer, helping stabilize the climate. But on Pangaea, most land areas were located thousands of kilometers from either the Pangaea Ocean or the Tethys Sea. Moisture could not penetrate far into the continental interior, and without the moderating influence of the oceans, the climate began to shift into an extreme state. Paleoclimate models and sedimentary evidence suggest that the interior of Pangaea may have been as arid as, or even more arid than, the modern Sahara Desert. During the day, the land surface absorbed heat intensely, causing temperatures to rise rapidly. At night, without oceans to retain warmth, the ground cooled abruptly. This contrast created enormous temperature differences between day and night, and between summer and winter. It was a world where life was forced to battle not only heat, but also constant fluctuations in temperature. Rare rainstorms created temporary lakes, but they quickly vanished beneath the scorching sun. This was not a collection of isolated deserts, but a vast arid belt covering the core of the supercontinent. Meanwhile, along the coastal regions near Pangaea and Tethys, moisture was far more abundant and temperatures were more stable, creating conditions favorable for forests to thrive. Fossil evidence from the early Jurassic indicates that coastal regions supported much richer vegetation than the interior, with denser ecosystems and significantly greater biodiversity. On Pangaea, change did not occur from one continent to another. It occurred across relatively short geographic distances on a planetary scale. But the most powerful force shaping the climate was not simply aridity. It was a global monsoon system. Pangaea was large enough to generate a phenomenon known as a megamonsoon. During summer, the entire supercontinent heated intensely, creating a vast low-pressure zone that drew moist air from the oceans deep into the landmass. By the time they reached the center of Pangaea, they had become hot and dry air currents. This was the climatic paradox of a supercontinent: seasonal flooding in some regions and prolonged drought in others. They directly shaped life after the Triassic-Jurassic Mass Extinction. Coastal organisms had to adapt to extreme rainfall and seasonal variability. Interior organisms had to survive prolonged droughts and severe temperatures. Each region became its own evolutionary laboratory, where only species flexible enough to adapt could endure. And within this extreme climate system, the foundation of the new Jurassic world was gradually taking shape. A Earth where weather, geography, and evolution became part of a single story. After Pangaea entered its supercontinental climate phase, Earth was no longer shaped solely by geography or temperature. The factor that now enveloped every aspect of life was the atmosphere. A layer of air that carried within it the legacy of the Camp catastrophe and an entirely new global climate system. Evidence from plant fossils, paleoclimate models, and geochemical isotopes suggests that the atmosphere of the early Jurassic contained carbon dioxide concentrations many times higher than those of today. This change did not turn the planet into a lifeless environment, but it was enough to intensify the greenhouse effect and keep Earth in a prolonged warm state, with almost no large-scale polar ice comparable to what exists today. The sky reflected that instability as well. In many regions, volcanic dust, sulfate aerosols from post-camp eruptions, and geological dust suspended in the atmosphere may have scattered sunlight more intensely. As a result, sunrises and sunsets may have lasted longer, displaying deeper shades of red and orange, sometimes appearing like a thin veil stretched across the horizon. But the factor that most clearly shaped life on Pangaea was the enormous temperature contrast between the continental interior and the surrounding oceans, which generated immense monsoon systems known as megamonsoons. During summer, the entire supercontinent heated rapidly, creating a vast low-pressure zone stretching across thousands of kilometers. Imagine a region along the edge of Pangaea. After months of drought, rivers have been reduced to cracked channels in the earth. Then, within only a few days, dense masses of clouds sweep in. Rain is no longer a scattered event, but becomes a prolonged sequence of storms capable of transforming dry land into a network of flood-swollen rivers within a short period of time. Sedimentary rock layers, preserved today in many regions that once formed the margins of Pangaea, still clearly record the alternation between drought deposits and flood deposits, the geological signature of this extreme climate cycle. But the farther inland one traveled, as moist air masses gradually lost their water during their long journey across the continent, they transformed into hot, dry air currents. Many regions in central Pangaea may have gone for months or even years without significant rainfall. Seasonal lakes appeared and vanished. Rivers shrank into brief and temporary flows. This was one of the harshest environments ever to exist in Earth's history. And it was within this environment that life was forced to evolve in new ways. Beneath the skies of Pangaea, weather became the dominant force governing life, turning Earth 200 million years ago into a world where the atmosphere, the oceans, and evolution operated together as a single system, continuously testing every organism that lived upon it. After the storms and extreme climate cycles of Pangaea, Earth 200 million years ago was not only different in its weather, it was different at the most fundamental level, its vegetation. Plant fossil evidence shows that ecosystems at this time were still dominated primarily by ancient plant groups such as ferns, cycads, ginkgos, and gymnosperms, especially primitive conifer forests. Flowers had likely not yet appeared, or had only just begun evolving in very early forms, and grasses had not yet become part of the ecosystem at all. This made Earth's surface look dramatically different from what we see today. There were no vast grasslands, no spring landscapes covered in flowers, and no grass-based ecosystems such as prairies or savannas. In the more humid coastal regions, forests could grow more densely, but they were still forests dominated by gymnosperms. In the arid interior, plant life was constrained by limited water, intense sunlight, and nutrient-poor soils, creating sparse landscapes that were almost semi-desert in character. A modern example that helps us visualize this world can be found in the remaining cycad forests of certain tropical regions today. They resemble prehistoric plants far more than modern vegetation. Rigid trunks, thick leaves, slow growth, and strong adaptation to dry or highly variable climates. On Pangaea, similar forms of vegetation may have dominated vast regions. But unlike today, they faced no competition from flowering plants or grasses, because those groups had not yet sparked their biological revolution. Studies based on fossil pollen and fossilized leaves indicate that plant diversity at this time was significantly lower than it would become during the later Cretaceous period, when flowering plants underwent their great expansion. This means that many ecosystems possessed far less structural complexity. There were no multi-layered grasslands, no seasonal carpets of flowers, and no ecosystems dependent on grasses like those that support modern herbivorous animals. Instead, it consisted of scattered gymnosperm forests, dense fern communities growing where moisture was sufficient, and vast open spaces between ecosystems. There were no grasslands stretching to the horizon and no seasonal blooms attracting insects. It was an Earth standing on the threshold of a great biological transformation, where ancient vegetation was gradually giving way to a future that had never existed before. After emerging from a world without flowers or grass, the Earth of the early Jurassic appears as a planet in the midst of completely reorganizing life itself. Dinosaurs had already appeared and expanded rapidly following the Triassic-Jurassic Mass Extinction. But one fact is crucial: they had not yet achieved absolute dominance. Fossil evidence shows that during this period, dinosaurs were only one of many large animal groups sharing the ecosystem. Within terrestrial environments, their competitors were far from weak. One notable group was the primitive crocodilomorphs, the distant relatives of modern crocodiles. At the same time, some surviving therapsids, descendants of the group that had once dominated before the Age of Dinosaurs, continued to exist in scattered populations, although they had been greatly reduced by successive biological upheavals. This reveals an important reality. The early Jurassic was not yet the age of dinosaurs, but rather a period of biological transition in which power was changing hands. So what allowed dinosaurs to gradually pull ahead? First was their body structure, characterized by an upright posture with legs positioned directly beneath the body. Compared with reptiles whose limbs sprawled outward, this design allowed dinosaurs to move more efficiently, conserve more energy, and was particularly well suited to the world created by Pangaea's climate. Second was their growth rate. Studies of bone histology indicate that many dinosaur species grew significantly faster than modern reptiles. This enabled them to shorten the vulnerable stage of life when they were young and susceptible to predation, while rapidly reaching sizes large enough to gain ecological advantages. Dilophosaurus, reaching approximately 6 meters in length, and serving as one of the earliest apex predators of the Jurassic, and the last surviving Plateosaurus, living remnants of the Triassic, slowly fading from existence. And even as they were gradually gaining an advantage on land, an even larger story was unfolding beneath the oceans, where the true giants of Earth 200 million years ago still ruled a completely different world. In Panthalassa and the Tethys Sea, ecological power was no longer an open competition. It had already formed true predatory empires. The oceans belonged to an entirely different evolutionary lineage: marine reptiles. Only a few million years after the Triassic-Jurassic Mass Extinction, approximately 201 million years ago, marine ecosystems began recovering rapidly from the periods of oxygen depletion and ocean acidification recorded in the global geological record. Vast ecological vacancies opened the door for an explosion of new groups of organisms, most notably the ichthyosaurs and plesiosaurs, two predatory forms that came to dominate the oceans of the Mesozoic era. Although they were reptiles, they evolved bodies remarkably similar to those of modern dolphins: streamlined shapes, highly efficient swimming fins, and impressive speed. Fossils such as Temnodontosaurus show that some species exceeded 10 meters in length, with enormous eyes that could reach more than 20 to 25 centimeters in diameter, among the largest eye structures ever known in vertebrate animals. Alongside speed and vision, plesiosaurs adopted an entirely different strategy. They were not the fastest pursuit predators, but masters of controlling space beneath the water. With forelimbs transformed into powerful paddles and robust bodies, plesiosaurs moved like birds flying through the sea. Some species evolved extraordinarily long necks, composed of dozens of vertebrae, allowing them to approach prey without bringing their entire bodies close. But these apex predators could not exist without the ecological foundation beneath them. And that foundation was built by ammonites, one of the most abundant groups of animals in the Mesozoic oceans. They were shelled mollusks, distant relatives of modern squid and octopuses. They reproduced rapidly, spread across vast regions, and became a central link in marine food webs, supplying energy to ichthyosaurs, plesiosaurs, and countless other predatory organisms. But the paradox of biological history is that the most dominant organisms are not necessarily the ones that endure the longest. Ichthyosaurs and plesiosaurs, despite once symbolizing the power of the oceans, would eventually disappear during later events of the Jurassic and Cretaceous periods. Meanwhile, on land, another story was quietly unfolding. Small creatures, largely unnoticed and dominant in no ecosystem, were beginning to develop traits that would completely transform the future of the planet. Beneath the layer of decaying leaves covering the conifer and fern forests of the early Jurassic, within ecosystems where dinosaurs were gradually expanding, lived animals only a few centimeters long. They were early mammals, such as Morganucodon, small enough to fit comfortably in the palm of a hand. Fossil evidence shows that these early mammals had already begun to develop a series of foundational characteristics. While many reptiles depended on their environment to regulate body temperature, these tiny creatures could remain active in darkness and under cooler conditions without entering a state of biological shutdown. Some indirect evidence from bone structure and comparative physiology suggests that they may already have evolved primitive fur. Initially serving as a sensory structure, it gradually became insulation. This represented a major step forward. For the first time in evolutionary history, a group of small animals could carry their own layer of thermal protection, independent of the surrounding environment. Studies of fossil skull anatomy indicate that early mammals possessed a higher brain-to-body ratio than many reptiles of comparable size. In particular, the regions responsible for smell and hearing were highly developed. This was extraordinarily important in a world where vision could not always be relied upon. From this emerged a transformative evolutionary strategy: nocturnal activity. As dinosaurs and many large reptiles became less active after sunset, the world turned into the domain of these small creatures. They hunted insects, worms, and other invertebrates in the darkness, navigating through smell and hearing. Paleontologists refer to this as the nocturnal bottleneck, a period lasting tens of millions of years that profoundly shaped the nervous systems of modern mammals. And as Earth continued to change with the gradual breakup of Pangaea, these nearly invisible creatures would become one of the most important answers to the planet's greatest question. After the age of giants, who would remain to shape the next world? Looking back at Earth 200 million years ago, we are witnessing a pivotal moment when the supercontinent Pangaea began to fracture, reshaping the entire surface of the planet. This geological breakup, combined with dramatic changes in the oceans and a harsh climate, created a biological filter that was both unforgiving and profoundly transformative. The catastrophic upheavals of the past not only helped shape the map of the modern world, but also stand as a testament to an enduring rule of nature. On a planet that never stops changing, life can continue only by adapting, evolving, and being reborn from the ruins. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.